We have one last example here in chapter 6 looking at uncertainty and information. We just saw several examples with separate equilibria, that is where different types receive different outcomes. The other possibility mentioned briefly but did not elaborate much on until now is what's called a pooling equilibrium. That is, all the types receive the same outcome. So here's what a pooling equilibrium might look like. So let's go back to education and workers again. Let's say that the productive types can produce 500 units when they're working, and the lazy types, not lazy time. Lazy types can only do 100. And say that there are 75% lazy types, so 25% of all workers are the high types, the productive types. We're going to keep the same payoffs as before. So the productive types, that means that the payoff is square root w minus 3 times e. And for the lazy types, that means that payoffs are square root w minus 7 times e. So if we're going to look at a pooling equilibrium, we're not even trying to separate lazy types from productive types. In this case, education just causes payoffs to go down, and we're not even trying to separate. You might as well set e equal to 0. So both high education and low education is going to be 0. So you still have to have that participation constraint to make sure everyone wants to work for you. So just to follow along with our earlier example, we said in our last example that the lazy types and the productive types can both get a payoff of 9 by working for someone else. So it's written on the participation constraint. We'd have square w minus 3e greater than or equal to 9, so the productive types want to work for you. And as both productive and unproductive types get the same wage and education, so I don't distinguish anymore between WH and WL, just W. Everyone's got the same outcome. Now I said back here I have to have education equals 0, since we're not going to use that at all. We're not trying to separate anymore between high types and low types. So what we're going to get is square root of w minus 3 times 0 greater than or equal to 9, square root of w minus 7 times 0 greater than or equal to 9. So it's just going to cancel out for both, which means that w greater than or equal to 81. That's our participation constraint. So you have to pay workers at least 81 to make sure that both productive types and unproductive types want to work for you. So I did include some extra information here in the problem. I told us what the fraction of workers who were productive types was, and also how much each worker could make. That's important because we want to make sure that paying workers 81 is profitable for the company overall. So take an average of these amount of output each kind of worker makes, a weighted average using the fraction who are productive, and make sure the company can at least break even. So average output per worker is we get 500 units for a productive worker, but only 25% are productive. So that's 500 times 0.25. Each of our lazy types produces 100, and there must be 75% of them. So they're 25% productive types. The other 75% must be lazy types. So you have 100 times 0.75. So that's going to be 125 and 75. That comes out to 200. So average output per worker is higher than our wage, so this is going to work. Paying workers at least 81 to get them to work for you is going to be profitable. So when I check that, we want to make sure that if the wage is, say, higher than output per worker, then it's better to just not hire anybody and just shut down your business. So that's how pooling equilibria work, and that wraps up chapter 6. Stay safe out there.